So in this little group of videos, I want to explore energy and energy conservation in space, especially for like astronomical scales. Um, so let me remind you of what you probably have already seen at smaller scales than astronomical scales. This is the scale of surface of Earth. So at the surface of the Earth, we basically have this acceleration due to gravity that is constant. I'll put constant in quotes because, or actually not in quotes, but I'll put approximately or something similar to constant. So if you stay close to the surface of the Earth, 9.8 meters per second squared is the acceleration of an object in free fall or a projectile. But only if you stay close to the surface of the Earth. You know that if you go further, do you remember this? This is the acceleration due to gravity at the surface of the Earth. This is the thing, oops, squared. That's 9.8 meters per second squared. But if you imagine what's the acceleration due to gravity at a radius r, where r is bigger than the radius of the Earth, what you're essentially calculating is this, right? And so if r is bigger than the Earth radius, then this acceleration due to gravity is, in general, smaller than g. That is, gravity seems to get weaker, right? The acceleration due to gravity is smaller, further away. But that's not what I wanted to describe. So if I'm down near the surface of the Earth, the acceleration due to gravity is roughly this constant value. Here's the Earth, and I can imagine doing some work to lift a box. And this work turns out it's the mass of the box times g times the height through which you lift it. That's the work to lift the box. Secretly, this is without changing the kinetic energy. So we're not allowed to speed the box up or slow it down, or we have to do so kind of carefully such that the kinetic energy at the beginning and the kinetic energy at the end are the same value. Yeah, so, but anyways, the work to lift the box is this mgh. The question is, though, is on an astronomical scale, what is the work to lift the box when h is something like the radius of the Earth? You know, so we want to go on the Earth scale, or when h is much, much bigger than the radius of the Earth. Like, take the box out really far, like what happens when you imagine putting a satellite up into orbit, or yeah, I mean, it's kind of crazy. You probably heard that maybe we could send all our nuclear waste into the sun. So like, what would be involved in firing a missile out with a bunch of nuclear waste on it all the way out so that it sort of leaves Earth's attraction zone and goes into the sun's attraction zone instead, and just continues to fall towards the sun. But you know, these are that kind of question. But if the acceleration due to gravity is changing or getting less and less and less as you take the box out, we don't get to use this formula. This formula is wrong when we're considering distances that are really, really large. So we have to go back and we have to think about this formula instead. And so, yeah, so we might start at a first place and finish at a second place, and this will be the work done to move the box from like an R1 out to an R2. So that's what I'd like to get to. But let's think a little conceptual about stuff first. So here is the situation that we all find ourselves in. So here is the moon orbiting the Earth in this elliptical orbit. And this system is somewhat similar to isolated. It's not isolated. The reason it's not isolated is because of every other planet in the universe. But let's approximate this thing as isolated so that the total energy of this little system stays constant. So the total energy of this little system is comprised of kinetic energy and potential energy. So gravitational potential energy in particular. The kinetic energy, it's really interesting, is actually the kinetic energy of the Earth plus the kinetic energy of the moon, right? Plus the gravitational potential energy in the Earth-Moon separation. It's the energy associated with the Earth and the moon being separate by a certain distance. That's that part. There are two kinetic energies because there are two objects that can have motion, but there is only one potential energy. There's not two potential energies. There's only one potential energy. It's the energy of the gravitational separation of these two objects. So this is pretty cool to think in this way. Pretend that what we had was Earth and the moon, but the moon had no sideways motion. Then what we have is these two things are attracted to each other. There is, or actually, let me erase this no sideways motion bit. We'll just start these two things off from rest. Right, so some big ancient astronomical being is holding these two things which are attracted to each other via gravity. They're just holding it apart, and then that big ancient being lets go. And then this is empty space. There's no friction, right? There's nothing else in the universe. Let's imagine them being isolated. So the little moon is attracted towards the Earth, and the Earth is attracted towards the moon. There aren't any other forces besides the attraction forces between Earth and moon. So these two things accelerate towards each other. There is a force on the Earth towards the right because of the moon, and there is an equal but opposite reaction force on the moon by the Earth, and they accelerate. This object is going to have the big acceleration because its mass is so small, right, by Newton's second law. This object is going to have a little tiny acceleration. So it's not going to pick up as much speed as the mass m is going to pick up, right? But so it kind of looks like this object picks up most of the motion, and this object doesn't pick up too much motion. That's the same thing that happens up here, except for these two things are headed sideways, tangentially towards each other. So what happens is, so the center of the Earth is here, and the center of the moon is here. It turns out that these two objects, they orbit a center there. That is the Earth. The Earth actually wobbles around that center, while the moon does an elliptical path around that center. So yeah, this is how this stuff works. So you can see that the Earth is wobbling as the moon wobbles around, and what they do is they just stay on opposite sides of that center, on opposite sides. All right. Okay, so this is the energy picture. Often, because the Earth doesn't really pick up much acceleration, the motion of the Earth is often ignored. That is, we say that it doesn't ever really pick up that much kinetic energy. So we say it's about zero. And the moon is mostly where the kinetic energy gets to shift around a lot. Okay, so, so going back to where we were headed before, I'd like to explore calculating the work done when the gravitational force is actually a function of r, right? So the force by gravity is going to be g, let's say m1 times m2 divided by r squared, right? And that's the magnitude of the attractive gravitation force that we're interested in studying. So let's imagine this situation. Here is, say, the Earth, and here is, say, the moon. And I know the moon, for us in our universe, the moon just is orbiting elliptically around the Earth. But let's pretend that we could imagine having control over the moon and having control over the Earth, acting like big ancient astronomical beings. And let's just imagine what would happen if I started with the moon at a certain initial radius. Let's say it's like, or let's call it radius number 1. So the moon and the Earth are separated by the distance r1. And I'm going to imagine what is the work involved, work to move moon from r1 to r2. So that's what I'm going to do now. So here it is at r1 from the center, and I'm going to move it out to r2 instead. So this work done is equal to the integral from r1 to r2. And so we have to be pretty careful. This is the work done. I'm going to consider the work done by an external force. So this is the external force. And I need to, so I'll do the dot product against moving out with small vector displacements, right? Starting here and then moving along a bunch, right? An infinite number of infinitesimal length dr vectors. So this external force, how do I understand it? Well, I'm going to choose F external to simply be the opposite of the gravitational force vector. And the reason I want to do this is because as I move the moon is attracted back towards the Earth by a gravitational force. I'm going to use an external force that has the opposite value of the gravity force. So here is this external applied force, right, by the big, gigantic, ancient astronomical being. And this external force is what I am considering the work by. And if I choose this, right, as the big being, I'm free to choose this. What this implies is that the net force on the moon equals 0. That's what it implies. And that means that the acceleration of the moon is equal to 0. That's by Newton's second law. And what this implies is that the kinetic energy of the moon does not change in this work process, right? So this is the point. I don't want to do any work to change the motion energy of the moon. All I want to do with this work is to change the location of the moon. I don't want to change the motion of the moon.